Hello, everyone. A very good morning to all of you. My name is Madhuri Chaturvedi, and I'm your moderator for today. I welcome all of you for our session for today, a deep dive into the safety process in aerospace and defense. Let me start off with introducing Fluid Codes. Founded in 1997, we are the authorized channel partner for ANSYS software, offering powerful simulation tools in combination with truly customer oriented support services. We have a team of more than 50 engineers focused on simulation, training, support, and consulting with strong technical skills. Now, I would like to introduce our speaker for this webinar. Megha is a skilled mechanical engineer and medium analyzed application engineer at Fluid Codes, specializing in system and functional safety engineering. Her deep understanding of system dynamics, coupled with her hands on experience in functional safety, allows Megha to address complex challenges with precision. Thank you for joining us today, Megha.
Thank you, Madhuri, for the warm welcome.
Before we start off the session, I would just like to highlight a couple of instructions. I would really appreciate if all of you stay muted for the entire session so that we have a smooth webinar. If you have any questions, feel free to ask them on the chat or in the Q&A menu. Recordings will be shared with all the registrations once the webinar has ended. I hope we have an informative session ahead. For any inquiries, please feel free to reach out to us at marketing@fluidcodes.com. Towards the end of the session, we will be sharing an evaluation link with all of you for us to know if the webinar went smooth for you. Since we have a lot of attendees just joining in, we will be waiting for another 2 minutes before we begin. Thank you. All right, I think we can start off. I would like Megha to take over from here.
Thank you, Madhuri, for your warm introduction. Hello, everyone. Good morning. Welcome to the webinar where we today deep dive into the safety process in aerospace and defense industry with respect to product development. So today's agenda, I will take you through risk and safety process, followed by the product development and industry application. And then we look into the safety development process with respect to V-cycle, which is industry standard that is being used, followed by what are the solution from the answers that will help you with this processes. And also we'll have a quick demo on safety analysis for electric vertical and takeoff landing taxi. So at the end of the session, you will be learning about a role of safety in aerospace product development, how it is influencing, and as well as how it is priority to have it considered during your product development phases. At the initial phases, it can cover from concept phase to the deployment phase, followed by the two-cell method for safety analysis and compliance that you will be using in the industry, how ANSYS can support with that, and as well as the best practices for managing risk in aerospace and defense projects with respect to your assessments as well as the certifications. Initially, when we think about the product development as a new product in the field of aerospace and defense, what are we considering? What are the phases usually the companies go through? As you can see over here, there is product life cycle. We have the concept followed by the requirements with respect to your customers or the industry or the application, followed by the detailed design of the systems and the subsystems, and then followed by our prototype design, and then to certify and qualify it, and then move into the manufacturing, then test the complete vehicle, and then deploy it, and also have the support for any of the diagnostic issues for the vehicle. This is how the product lifecycle works with respect to the product development in the space and defense industry. Let's first understand the conceptualization and requirement definition. So in the requirements, it's nothing but the vehicle, what is the functionalities it's going to perform, especially with the requirements, what are you building the component for, what's this end use. The requirement detailed analysis is being focused in the requirements, followed by we have design and prototyping. So in the design and prototyping for the functionalities and the requirements that you have defined, you will be designing a system, subsystems, and components. If it's the OEM, it will be defining a system, what is going to perform, followed by its subsystems, what are the subsystems it will be having. For example, it can be hydraulic, mechanical, electrical systems. So all these are subsystems which is present in the vehicle, followed by the components. If it is a tier 1 or a tier 2 supplier, you always go with the components. What are the electronic components? What are the actuators? What are the sensors you're going to work on it, or is the PCB designs. So if you have tier 1 and tier 2, work on this. So the design process changes from an OEM to tier 2, but the product lifecycle remains the same for both OEMs and as well as the tier 1, tier 2 suppliers. And then we have prototyping. Once the design is finalized and it's been released, we go for the prototyping, where we have the detailed design, and then we have the prototype and just go for next is the engineering testing for the prototype which has been developed, followed by we have the testing qualified and we go for the certification with compliance with authorities like FAA or ESA, which are European Space Agencies, or with the FAA, which is Federal Aviation Authorities. Then we go for the manufacturing and the production, followed by the production deployment and the maintenance. So this is the process. Let's now focus on the industry specific challenges that aerospace and defense companies are facing at the moment. Initially is the high cost because it is a research and development investment and followed by the long development cycles. So why it is happening initially? Because one is having no clear defined requirements, or not having a clear defined functionalities, or at the design stage which is not a very detailed design or the architecture which is provided. And also there is always why it is a long development cycle. That is always it's done in a series manner. You have the requirements, you have functionalities, you have design, then you go for prototyping. So is there any solution that you can do in a parallel way, that you have a requirement which is given to multiple teams and they all work along? So it will shortcut your long development cycles to the smaller one. Next, what is the next challenge that industry is facing right now? The regulatory challenges. That comes into picture when the deployment of your system is going to be at the different regions in the world. So to have it qualified with respect to the certified authorities, you have to go through the certification process. So for this process, you have to define a process with respect to the industry standards that has been defined from these agencies or the companies. We have technological complexity. As of now, we know we have now unmanned systems, completely battery operated systems, which are prone to cybersecurity attacks, safety analysis attacks, and as well as the risk and hazards are much more when compared to the existing or the previous vehicles. How do we tackle this? As well as when there is a complexity in the technology, there is also comes the complexity in supply chain, because you require different type of systems which is more advanced. So initially, if you have not defined your systems in a clarified way, you will not be able to give the requirements to your suppliers to have a supply chain within your required time. So you are spending your money, your cost, as well as both of it to have a supply chain continuity. Then safety and reliability. As I already said, because of increasing number of systems with respect to electronics and the software in the vehicles, there is always a high risk for safety and reliability issues. Because one is at safety, there is always could be attacks, all the failures of your systems in increase, and probability also can increase of the failures. And reliability is always how you maintain access and reliable, you make it a quality reliable product as well with these multiple components. Then comes the at last it comes for the market competition. So here about this is having a process, how fast can you enter the market with a defined process, and without a defined process, how it is difficult to enter the market. So for example, if you already have a certified product, it's very easy to enter the market and you're not restricted to any of the region and you can supply in all over the world. And for example, if it is not a certified product, it's only for one or two customers. It's always is going to be the depending on that customer itself. You don't have the capacity to deliver this product worldwide or scale up your projects. So this will reduce your competitive, it will increase the competitiveness in the industry from your point of view, and as well as the market pressures to deliver the product in the deadlines from the OEMs if it's a tier 1 or tier 2 supplier. So this is the basically the industry challenges that we are facing as of now. So let's see how in the current from ANSYS as well as the industry, how they have defined the processes that can help with all these challenges. So as I was saying, this is completely about the initial phases of product development where we come across the risk and safety of each of the subsystem that you have defined in your initial stages. So it all starts from risk. So what is risk? It is the likelihood that a hazard's potential to cause a harm. For example, there is an electrical failure, there is a hydraulic system failure, or mechanical system or electrical wire failure. So these all the failures is caused by a hazard. And then safety is a condition where when the risk of the harm and damage is limited to a acceptable level. So following this processor, if we are not saying that you are eliminating the failures 100%, we always say that the failures are present but at a acceptable level. To understand that, let's focus on what is hazard in the first place or why the hazard is caused. So hazard, as I said, is nothing but a failure is a result of a fault in your systems or a component. It leads to failure of your system, which leads to the hazard of your system. So this hazard will cause the damage for your function of your system to perform. There are two types of analysis that we do for this. One is the functional oriented, that is if it is performing as per your requirements or your functionalities, or we do a detailed design system analysis where we see what are the failures in your system with respect to each of the components. As I said, your systems here or subsystems here means the power systems, the sensors, the uh, power distribution units, or the control systems. So you walk through the design and the failure that can occur from the subsystems, or you walk through the functionalities of each subsystem is supposed to perform and how they are failing, how they can fail. So this all analysis is done at conceptual level. Even when it is done at a conceptual level, there is always something which is at the end of the day, it's always there a fault. So that fault which is not being mitigated with respect to all the safety processes, we call it as a residual risk. It's always there. But how it is mitigated is with respect to control measures. This is where the reliability, accessibility, maintenance, and serviceability comes into picture, followed by the avoidance. So we can introduce some avoidance measure to make sure our faults are not caused, so that there is no hazard and there is no interruption of the functionality. As I said, it's as low as reduced risk. So when it comes to the functional hazards, we have preliminary hazards and then operational studies followed by risk assessments and functional hazard assessments and failure motion effective analysis. So all these analysis are done at 2 points. One is at the system level, your complete vehicle, and second is at your subsystem level. All the functionalities being defined for your each subsystems and each functions is being put into the operational situations and then followed by the analysis. And then on the right side, as I was saying, the design analysis, it's basically two types of analysis for your failures. One is quantitative, one is qualitative. In the quantitative, we say what is the probability of the failure of the each system. It comes to the qualitative, it's always the modes of failures, how it is going to fail. Is a communication failure? Is a electrical failure? Is a mechanical failure? Is a fire hazard? What is the type of qualitative analysis? Industry application has a set, as it is a aerospace related industry for respect to safety. We have ARP standards. All the processes that we have defined in the last slide are present in defined by industry with respect to the standards or the product that you are building. So if it is respect to the human interactions or humans has been present in the development of your product, you always have to consider ARP standards, that is aerospace recommended practice, which is given by SAE. So safety of automotive engineers, they have given two standards, that is ARP 4754 for the complete civil aircraft development and systems, followed by ARP 4761, which is for safety assessment. So these two standards always go in parallel for the development process. Next segment is our satellites. So here we have unmanned satellites, we have manned satellites. So over this, you can choose if it is with respect to your safety of the astronauts or with respect to the reliability of your functionality of your satellite. For that, we have space product assurance, which is respect to safety and quality, which is defined by European Space Corporation and also which is given from European Space Agency. When it comes to military standards, if you are developing a UAV with respect to military standards, there is all military standard which is given from Department of Defense, that is MIL standard 882, which is respect to system safety. When it comes to military, we always concentrate on the reliability as well as the failures and the effect of the failure in the terms of cost, because there is no human interaction which is considered with respect to the military standards. So this is the difference how you can use the above hazard analysis of each of it with respect to different applications with in the aerospace and defense industry. So for today, we'll be taking up with respect to the ARP standards. As we were taking through what is the process, how have we have to define the standard processes which has been given from the aerospace industry. So there will be, that is we call it as V cycle, where we place all our analysis at each level. For example, at the concept level, we have hazard analysis at the concept level, which is at the vehicle, which is very high end level. Then we have preliminary design and detailed design for your systems and subsystems, and you allocate all the hazard analysis and to your system subsystems, followed by your implementation at hardware and software level. Then we have system verification and integration. Over here, once you have developed your systems, you integrate them back to your aircraft or the air vehicle, and then you test the systems. So this complete V cycle is been is the industry standard as of now and also followed one. So here you can see it is given in the V shape, which is it's not a series, it's a parallel activity. So as we were discussing about initially, it's a long development cycle. So this is one of the solution from the industry standard that we have currently with respect to this product development. So if you can see here, this V cycle represents a parallel activities that can take place at each level. It's not a series activity. So it will reduce the time, the cost, as well as the integration time as well, because you already you have a very defined functions, your requirements, your subsystems, they all go under the integration and testing before they go into your vehicle. So if it is for OEM, you always have defined requirements from your suppliers, and also the quality is meeting as per your requirements that you are procuring from your suppliers. If it is for a suppliers, you are always delivering your product with the quality with respect to your OEM standards, industry standards, as well as with your requirements with OEM. So when there is the quality check going out of tier 1 or tier 2 suppliers, there is no issue with the quality, and with respect to OEMs, when they are importing the or buying the off-shelf products, there is also no issues with the quality. So where this application of these standards as well as followed by the process at any level of the product development will ensure the time and the cost is reduced between the companies as well as the suppliers and the OEMs. This is the only way where we can develop with respect and then optimize the processes. That's how the industry has defined the standards and the processor. So it is applied all over the world without any restrictions with that. So let's now discuss how ANSYS will support you guys with this industry standard as well as with the safety processes that is present. So we have solution in ANSYS where in a single platform you have the requirements and then you import the requirements, define the functionalities, predict the hazards what you can see, define a safety requirement for that hazard, continued by your complete system and subsystem architecture, and also the failure prediction for the architecture or failure prediction for the hazard analysis or your subsystems, followed by you also have FMECA, which is respect to the failure modes, how your systems are failing, not only how quickly they are failing, but also by which mode they are failing, where you can introduce your safety mechanisms to reduce the probability of failure. Followed by you have your reliability, which will give you with respect to especially the hardware and hardware tier 1 or tier 2 suppliers, where you can predict your reliability and also make sure the quality meets. And then you also have your safety case compliance with respect to the certification processes. At the end of it, you always have a report that you can directly submit to a certification authority so that you can show all this compliance has been done with respect to a qualified tool with the help of it, with the help of qualified tool. Which is present with the answer solution, followed by all the process which has been defined from the industry as well as with respect to standard. So the covering of these three aspects is the solution that ANSYS gives to you with respect to the safety and reliability of a development of a system. So how this work, how is going to help at the initial level? As I said already, it's going to reduce the cost, the time, as well as the effort that is put into this. When there is a detailed initial concept clarification followed by the detailed design, there is always a possibility that the product will be into the market within the given time without any delays. Let's this is about the safety process. So let's just I will take you through one of the example how it works. So today we will be taking you through the Medini application with respect to the electrical vertical and takeoff and landing taxi. Here we will be taking you through the system functions followed by the model. How do we model the our vehicle with respect to the functions that has been defined, followed by the guide word analysis for each of the function and to predict the failures, and then followed by the functional hazard analysis, and then design assurance level for each of the functions when there is a malfunction which is present with that. Next, we will be taking you through the functional traditional fault tree analysis, which is FTA, which is qualitative and as well as the quantitative analysis at the system level, where we will find the root cause for each of the malfunction that we are predicting. Then we have a FTA evaluation followed by system requirement generation for each of the failures. When we go to the component level, we have failure mode effective and critical analysis, followed by reliability prediction, that is specifically with the failure rates for each of the component, followed by the common cause analysis, because in the system we have different system, we need to see failure of each system, how it is going to affect other systems in our vehicle, followed by safety case compliance, where we will see the complete safety analysis process. Is it up, it is done as per the industry standard? Is it okay to go with, can we produce the documents to the certification authority or to the OEM or to the tier one? So when you're, this helps, the safety compliance will give you a complete a box of information how your safety process has been taken place in your organization. So all this can be generated automatically with respect to ANSYS solution. So this at each stage of the air vehicle system, subsystem and component level, all these documents can be exported and it is qualified as well. Let's go with air vehicle analysis. In the analysis, first we define systems and subsystems followed by functions. So here you can see in our example, we have quad rotor aircraft. We have four rotors over here. So we have list system, we have battery system followed by navigation, and we have aircraft structure. We have fuel gauges as well as the landing gear and cabin and interior. So as you can see, this is our system, which also consists of our other subsystems. If you see the system functions over here, so let's take lift control system. You need to lift the the functionality that we are defining over here is to lift the vehicle, move to a certain place and then land over there. So this is, let's take this one of the function that the air vehicle has to perform. For that, the lift system is also responsible for that. So let's take one of the function of it, provide vertical lift control. So what, to perform that, it also requires the help of other subsystems. It's interacting with other subsystems. How it is interacting? It requires power, it requires position, it requires torque. So these are the subsystems which is present, you define in the form of a net where all the dependencies is given for your system to function. Once you have defined the function, we come up with the guide one analysis. So why this guide one analysis? For each of the function that is you have defined for your system, you need to see where can be a loss of that function or improper functionality, or there is no functionality at all. So for this, to make sure your guide words are defined by the standards, so you are having a guide word for each of the function which can be a predictable malfunction. Over here you can see we have a list of functions and then malfunctions. So one of the example is provide high voltage DC power to the electric motors. But if it doesn't work, the complete HV battery is failed. This is one of the possible malfunction that we can predict at the very initial stage when you define about system. Then if it's not a total loss, it can be a partial loss. We can always expect this from the systems. So individual portion of the HV battery will fail. So this is our predictable malfunctions for each system that we have defined. So at the end of the vehicle level analysis, we always come with the well-defined functionalities. We have a high-level architecture where we have stakeholders from different teams who can look into it about the functionality of your complete system and also work with you for the malfunctions. What is the predictable malfunctions we can define at this level, followed by the guide one analysis. So once we have the guide one analysis, we go to hazard analysis and design assurance level. So how are we going to do this? How it is defined from the standard? In ARP 4761 standard, it is given from this table. Here, based on the hazard of or the failure of your subsystem, you will be considering that, you will be rating that hazard. Either it can be catastrophic hazard or it can be hazardous, it can be major or there is no safety effect at all, or it is a catastrophic. Not only that, if the failure happens, how long can your vehicle sustain also will be considered over here. So we have the function, we have the condition, how the failure can occur, followed by the phase. phase is nothing but the operational situation that we were focusing in the earlier stage. The operational situations, as I say, the operational situations for this vehicle is to take off, cruise, and then land. So this is your phase of operations. So you make sure all your systems and subsystems are working efficiently at each level of phases. That's how the hazard analysis takes place with respect to a situational hazard, situational operations, followed by the effect of the malfunction if it occurs in your system. So based on that classification and also effect on the, either it can be effect of the aircraft. If we are having an unmanned aircraft, then what is the effect on the functionality of the aircraft? If there is a human interaction with respect to the aircraft, then with respect to how is the hazard is caused to the crew which who are present in the vehicle. So based on this effect, you will classify it as per the catastrophic. It's the highest possibility of hazard, where we say there is a loss of life or there is a complete destruction of your aircraft. It comes to hazardous, this is the emergency landing, which may be with the minute, uh, may not the fatalities. So there is no fatalities, everybody is safe, but there is a hard landing. Then followed by your major, where the crew is uh, not able to stop the aircraft or resulting which will be low speed contact with respect to terminal or vehicles, something like that. When it comes to no safety effect, there is some failures we don't consider as a part of safety. So for example, if there is uh, a minor, there is, for example, if there the seat is broken and is not able to, is already able to land, and the seat is broken but there is no effect on the cabin crew or the crew which is present in the aircraft, and also not the functionality of the aircraft as well. So what do we do is we don't consider as the safety perspective, because it's not affecting, either it's not affecting the humans which is present or the aircraft functionality. So this very minor failures we don't consider for the safety. So let's see how in answer solution we have defined. So this is the standard. On the right side, you can see what you're saying is the standard. When you are performing, there are multiple factors we need to consider for each of the functionalities, which is a, which goes here we are dealing with respect to either cost or human lives. So we have, it is a critical analysis that we are doing. Over here, we have the functionalities followed by the malfunctioning behavior that we have derived from the guide word analysis. Then we have phase of operation, how where the malfunction is taking place at which level of operation. Then we have the failure conditions. If this malfunction is happening at this phase, what is the failure condition? Followed by the crew awareness. Are we able to alert the crew or not? So what's the effect of failure on the aircraft? Followed by the occupants. What is the effect on the occupants as well? Then we have failure condition classifications from which is respect to standard. Then we comes to the FTAL, which is nothing but your design assurance level. For each of the functions, you define the design assurance level with respect to your hazard. So this will give you the components of complete how your system has to be developed, or how your system has to, it will give you the, one is the safety requirements at the end of it when you do a hazard analysis. So let's just take one of example that would be much better over here. So let's say the one of the functions we have is convert the electrical energy to the shaft torque. So combination, we are taking the malfunction as any combination of dual propulsion failure. So which this will affect at all operation phases of operation, not only takeoff, cruise, land, it is going to affect at all. Followed by what is the hazard? If this malfunction happens, what's the hazard? The dual propulsion failure takes place. So are the crew is aware or not? Then followed by the effect of the aircraft, that is the hard landing, because there is no propulsion, there is dual failure, so it will be a hard landing. So what is the effect on the occupants which is present in the aircraft? So it's potentially multiple occupant fatalities. That's why we consider it a catastrophic. So all the FDALs over here will be automatically generated from the ANSYS solution for you when you define this functionalities. So you don't have to refer each time back to your standard to define this for you. As well as the comments over here will give you what is the safety requirements that has to be done or taken care. Next comes is the safety requirements. In the safety requirements, operational analysis for each functionality will be given, followed by the malfunction and defining safety requirements. So initially in the last slide we saw we have defined the assurance level for each of the functions. For each of the function defined, we derive the safety requirements. So this is not supposed to happen, right? The dual failure is not supposed to happen is one of the safety requirements. Once you define the safety requirements, then you can automatically tag it to the analysis that is required to be done based on your FDAL. So if your FDAL is A, then you have to perform what kind of analysis to see what is your failure rates or your root causes for that failure. So what kind of analysis you need to do is defined from the standard that is already been placed in the as a solution. So output of this is basically the FDAL for each system. You know how critical is your system is and how it is supposed to perform, followed by your safety requirements for each of the systems and how you have to develop it and test it and then integrate. So this will takes place at all level of the development process. All these test cases will be continued, all these safety requirements will be met at each level of the product development. Then followed by you have safety and assessment recommendation for each of the safety requirements based on your FDALs. If it's a A, if it's a E, or if it's a D. So how are you gonna work on this? Which safety analysis method you need to imply for analyzing that subsystem? It is a faulty analysis or you are doing failure analysis. So this is also defined over here. Now we have the functions and malfunctions. Let's define our architecture of the system. So with respect to functions, this is how the architecture of the system has been defined. Here you can see all the higher level systems is represented, as well as you can see the interactions between them, how they are interacting with their subsystems as well. And over here you can see the complete architecture of the system, which can be an output for your tier 1 or tier 2 suppliers or an input for tier 1 tier 2 suppliers from their OEMs. This is basically done at any level. This is for the system level activities. So system level who is ever working on it can define a complete a detailed architecture with respect to the systems with different stakeholders. When we have this architecture, we need to know how this our components are going to fail, all our subsystems are going to fail. How can we predict that? We have analysis, safety analysis. One is faulty analysis. At the faulty analysis or system level, we define top level hazards, and then we find the failures in the subsystem and why the subsystem is failing and what is the root cause of it. Here you can see how the safety requirement is being traced back to the hazard, followed by the failure, and then also followed by a system failure, a subsystem failure, followed by your component failure. On the left side, you can see the probability of the failure as well. So here also I would like to mention that this probability analysis as well, we have templates which is well defined. So at the end of the faulty analysis, you always come up with a root cause for your failure of the each system and probability of failure and then failure propagation. So ANSYS tool will give your propagation failure from your top level to your component level. As I was saying, the propagation of failure here you can see in your architecture as well, where it is easily predictable how your system is going to fail and what are the subsystems is caused due to that. Next, we have failure mode effect analysis. Now we know the failure rate at what it is going to fail. Now we need to know how it is going to fail. So we can directly derive an failure FMECA worksheet from our architecture with ANSYS solution, where you can find the failure mode for each function as well as failure rates that would be over here, which is shown. So on the right side, you can always see the functions, the components, how it is going to fail, as well as what is the potential failures due to the component function failure, and can we detect it or it is not detectable, or if it is detectable, can we ensure that it is covered, it is diagnosed, or can you make sure this is being given as a signal to the crew which is present. So all this type of analysis for each function is done at the how it is going to fail in FMECA. And also over here, the main thing is the potential failure causes. Why, if it is going to cause, you can see on the right side over here, if the cooling fan is one of the failure that is happening, which will directly affect the functionality of this. So for each of the function, you are defining the potential causes at your level. So you see the type of analysis we are doing over here. It will give a complete all level of analysis for your complete system. You have component, your system, your subsystem. So it will help you to choose better components or design a better architecture for your subsystems, or to work on your requirements to meet this. So you can always go back to your requirements to ensure the safety requirements are met. On the below, you can also see determination of failure rates. So we use handbooks for, especially with the hardware development. So ANSYS Medini already have handbook which is from different industries. It can be from the military background, it can be from the machinery, it can be from the aerospace background. So we have multiple prediction analysis as well as the handbooks which is present. We can just have it downloaded and then we can perform complete failure analysis or reliability analysis for the hardware part. Next, we have the dependency tree, where you can see how each of the systems are failing, how it is affecting for the top activity. Followed by we have a net and also requirement, which it will show us that in the form of a visual representation, how the dependency, the functionality of each is depending on the component. So at the end of FMECA, which is very critical in the aerospace industry product development. So what are the outputs we are going to get? The failure rates for each component, followed by probability of your failures, how fast is going to fail in number of hours of operations, and failure propagations, followed by failure dependency net, how each of your components are interdependent on this. This also can be given, also works as a document that you can give it to your software and hardware teams in the working environment, which acts as a HSI document for them. When we are talking about the analysis, there is also common cause analysis, which is basically apart from electrical system, power distributions, and that we also have mechanical system, hydraulic systems, and electrical. For example, if there is a fail in electrical system, multiple systems will fail in our vehicle. So this is part of common cause analysis. Due to one failure, when there is due to one risk, there is multiple failures which is causing to the multiple hazard at once. So this is, we call it as common cause analysis. So what it gives you, this evaluation table which is already predefined in the ANSYS solution will give you how you have to make sure all these common cause analysis are not present, which are not dependent on each other, and then also identify it and also see the effects of it. Here you can introduce a redundancy. That's how. So when there is a common con analysis, we are identifying it and you are reducing it. You are reducing the interdependability of your subsystems on each other. You introduce a safety mechanism. So if even though there is a failure, at last your functionality is there. Not maybe not 100% it's not functioning, but maybe at 80% or 70%. If we are able to achieve it for each of the systems or the component or functionalities, that's going to make a lot of difference with respect to the quality and reliability of the system. At the end of it, we have done all these safety processes. So once we are going for certification process, we have to make sure that all this as in the part of documents. So this is where it comes into picture that this Medini will give you, have you completely evaluated your all safety processes as defined from the standard or not. Here you can see for each of the safety requirement, you need to fulfill it with respect to your probabilities. Only if you have completed all the steps and all the recommended practices for safety, then only it will give you a green, which means this safety requirement is completely satisfied. If not, you have to go back and rework on that. So why is this? It will make sure that no safety process has been left out of it, or you have made a mistake at any point of development process, and also to make sure that the quality is met as per your requirements, and also there is a traceability between the functionalities, and also followed by especially the which is the main important is your DAL, which is for each subsystem design assurance level. So all this is met and your complete product has been developed with respect to industry standards as well as with a qualified tool. So this will give you the continuous evaluation of your complete process or a development phase, which is a detailed development phase. And also it will help you with the complete safety analysis lifecycle. So as you can see in the single platform, you are able to see all the all the things from the initial requirement till end of the deployment as well. So in the conclusion, what Ansys Solutions gives to for your existing work process? A complete concept modeling before you go into the manufacturing process, which will help you with achieving real-time deliverables. Followed by your MBSE, because MBSE is a state of art as of now with the industry. It's all model based, as you can see. All stakeholders can participate. There is no mentioning of complete technicalities in depth. It's always about functionalities that you do. And then because it is a MBSE based process, it is always tailored with industry standard and is a defined standard process. Then we have reliability and prediction analysis, which is also a scalable analysis, either from your component level to system or subsystem or complete vehicle level. We have the traceability and validation, which is especially with respect to the quality of your product. We have teamwork and review support with respect to, as you see, an SSC at the last. So it will give you a teamwork, how the process is going on. And also we have other tools which you can integrate with respect to answers with Medini as well. And also we have requirement tools which can be also be integrated like doors with respect to Medini. And we have a reporting and documentation. So this is basically helps with the certification process that we discussed initially. And with respect to add to this, there is also a time and cost reduction in procurement because it's well defined projects and well-defined missions. And it will speed up your certification process and time to market. So that will decrease your competition in the real world where you can enter into the market. And also with this certification, the important thing is your OEMs which you are supplying, they are confident that you are using a qualified tool a qualified process, so the quality assurance will be high. And then it will reduce your iteration process that we do for testing and validation at your bench, which will highly save the time as well as the manpower used, followed by the cost. So when you use a qualified tool which is already having a process well defined, all these steps can be reduced. So this is going to help you to complete, you reduce that long development cycle, detailed designs, and then move forward with your manufacturing. So this will speed up your complete concept and detailed design phase. That's how ANSYS solution is helping you at the system levels.
Thank you, Megha, for that very, very informative session. In the interest of time, we are taking just one question and we will be closing the session. I have also shared the feedback form for this webinar with you all on the chat. So I request all of you to fill the feedback form with us. It will take maximum a minute for you to do it. Can we have a question from the audience, please? We'll just take one. Mohammed Afifi, maybe you can type in your question in the chat. You can unmute yourself.
Okay, I will take one of the question, which is how do human factors contribute to safety risk? So here we are not considering human factors because we are looking for the safety of the humans in the first place. So we are always working on the safe, how safe our and reliable our vehicles are with respect to safety, not with respect to the human factors. So we are not consider human factors or any of the human faults that we can make in the system. No, it's always about the how our vehicle is functioning.
Yes, the recording of the session will be available afterwards. We will be uploading it on YouTube and the link would be shared with you.
So the next question I would like to take is what are the potential hazards in the systems or operation? As I said initially, it can be your mechanical hazards or it can be electrical or it can be hydraulic hazards. So hazards we can be in the form of any systems or in any systems. So this can be the possible hazard that we usually encounter. It all depends on how what the components are in the vehicle, how we have defined our architecture.
All right. With that, we would like to wrap up the session. I hope all of you had a wonderful session. And if you have any inquiries, demos, questions, anything, you can reach out to us at marketing@fluidcodes.com. We would be happy to help you with any of your inquiries, questions. To stay up to date with our latest information, content, webinar, please follow us on YouTube, Instagram, Twitter, and all our social media handles at Fluid Codes. Thank you so much, everyone. I will hope you all have a great day ahead. Thank you for joining us.